Good morning to everybody. Apologies for the short delay. We are at the third masterclass of this workshop, and the speaker is Professor Alina Mattei from the University of Neuchâtel, Switzerland, and she will speak us about the generalized calibration for no-response and non-probability samples. Alina, the floor is yours.
Thank you very much. Is it okay if I speak like this? Okay, great. So first of all, I would like to thank organizer for the invitation, and especially Alessio Guandalini, who wrote me. And probably to make a balance between, let's say, the first day and the second day, Alessio asked me to talk about calibration. Okay, so I don't talk about calibration, but I will talk about something that is less known and called generalized calibration. And you will see that in my talk, I will make a mixture between a lecture and a presentation, because this is my idea about the masterclass. But I have a technical problem. It doesn't work. Please help me. Cannot change the page. Oh, it's okay? Yeah. Okay, great. Up and down. Yes, okay. Thank you very much. So I will start with the contents of this presentation. So first of all, I will introduce a no-response framework. I will give a small introduction in this topic related to generalized calibration for handling non-ignorable no-response. I will talk a little bit about latent variables in connect generalized calibration, and I will provide the extension to non-probability samples, and I will conclude. And you'll see during this presentation that I will create a bridge between the three main important topics. So non-ignorable no-response, latent variables, and non-probability samples. Okay, so as you know, missing data arise in surveys under two main forms: unit no-response, item no-response, and we are interested here in unit no-response. And of course, no-response can create bias in estimates, and we are not able to completely eliminate this bias, but one tries to reduce it as far as possible. And as I said, I will focus on unit no-response and bias reduction, but of course also the variance reduction is a feature in this problem. And I will use the classical notation. Capital U is our final population of size capital N. A sample S is selected from this population using a sampling design in the beginning. So pi k is first order inclusion probability of unit k in the sample. And I will assume that all the first order inclusion probabilities are positive. Y is our variable of interest. And we also assume that we have a vector of auxiliary variables, which is assumed to be available for each survey unit k in the population, or at least in the sample. Concerning the no-response framework, as usually, we see this set of respondents of a subset of S. And we use the classical two-phase approach. The set R is seen as a random sample selected from S using a sampling design. And we suppose that Y is observed only on this set as missing for the other units outside of this set R. We also use the classical indicator R, which is 1 if an unit answers a survey with a probability of response. And again, I will assume the probabilities to be positive. And here we are interested in what we call the non-ignorable no-response, where the response probability depends on the variable of interest. So I can have the forms that are given here, where this probability depends on Y and X, or simply on Y. And this is typical for the surveys with what we call sensitive topics like income, drug abuse, politics, sexual attitudes. And the problem it's difficult to manage because, as you see, the response probability depends on the variable of interest. The goal is to estimate, for example, the population total or the population mean. And of course, without non-response, we can simply use a horizontal for the population total, or we can use, in the case of the mean, the horizontal estimator or the Hayek estimator. And now we are interested to introduce the notation of the weights. So in the first moment, we use di to be the inverse of the first order inclusion probabilities, to be the weight which is associated to a unit in our case. And the goal is to adjust the weights. So we divide the initial weights by the response probabilities by assuming them to be positive. And in this case, we use what we call estimator adjusted for no response. So for the totals, the horizontal type estimator adjusted for no response, where we take into account at least on the theoretical levels probabilities, the response probabilities. Or for the mean, we use the Hayek type estimator, which is known to be more performant than the horizontal estimator for the case of the mean. And of course, the main problem is here, the response probabilities are unknown and they should be estimated. And the problem is that we are working in the case of non-ignorable no response, so it's not so easy to estimate the response probabilities. But if we are able to do this, next we compute the two estimators which are given here, where we replace the response probabilities by estimated response probabilities. Okay, and just a small slide about calibration. Everybody knows the idea of the calibration. So without no response, we try to create new weights, W, which are close to the initial weights, because we minimize the distance between the new weights and the old weights, satisfying what we call the calibration equations, which are given in equation 2. And in this case, one uses a function f, which suitable properties, like a linear function or an exponential function. And this vector lambda is a vector to determine by solving the calibration equation given in 2. And finally, the weights are denoted by W, takes into account the initial weights, and this factor f, the adjustment factor f. And we construct our, let's say, calibration estimator for the mean by taking into account in this moment the weights W. Okay, in the case where we have what we call marked no response, so the response probability depends on X. What we have in this case, we have two possibilities. We have, first of all, the method of two-step approach, where in the first step, we estimate the response probabilities by using a logistic regression model. For example, and we form the intermediate adjusted weights di over pi I hat. And in the second step, we obtain the final weights by calibrating. Okay, and the final form is given here. We can use calibration by using the population totals or the values of the estimators using the sample. And there is the second approach, called one-step approach, when we obtain the final weights directly, and we assume that in this moment, our final weights are given in this form, okay, di times the adjustment factor, such that the calibration equations are satisfied. And in this moment, we assume that this f is simply an estimation of the inverse of the response probabilities. And the same response probabilities are used in the adjustment factor and in the calibration equations. I underline this because you'll see afterwards that is not anymore the case. And in both approaches, we construct our estimator using the weights, and the estimator is given here for the mean, and we observe that we use the units on this sample, on this subset R. Okay, now what is generalized calibration? In this moment, we compare with one-step calibration. Why? Because the form is similar, but we have other variables. Okay, so in the beginning, in the classical one-step approach, we have the calibration variables which are included here in the adjustment factor. Now, in general calibration, we have another set of variables, and I make the distinction between two because I will use this notation with Z now. And I will call the first set X to be the calibration variables, while the second set model variables. okay? And okay, it is possible to have an overlap between the two sets, but here I will assume that they are completely different. And in this moment, of course, the calibration equations should be fulfilled for the general calibration, but we can underline the difference between the previous case because we have the Z variables and we have the X variables. And finally, our general calibration is similar to what we have seen in the case of calibration. And I would like to make an important remark here. There are two different points of view, okay? If you see here, I use model with quotes, okay? Why? Because this is the point of view of Deville, who introduced this method in 2000. I give here the reference in English. The reference in French is 2 years before. And the method was rediscovered 6 years afterwards. And both think that finally, what we have here is simply a functional form F that is introduced in our case, and there is no response model. While it is a second opinion that is, for example, given in the paper of Aziza and Beaumont in 2017, where here we have model variables without quotes because the calibration equation is seen as an estimating equation. Okay, so there are two different points of view. Okay, now in this slide, I will use the quotes. Why? Because it is the idea of Deville. And you have seen that the values of the Z variables should be known only for the respondents. And the idea of Deville was simply to use Y. So Y in this moment is a response variable, but also the variable of interest. And this is very appealing for the case of non-ignorable no response, as I indicated in the beginning. So we can assume now that I have this form of the response probabilities, okay? And I will underline some features in the case of one-step calibration and generalized calibration. First of all, the choice of F is very important in one-step and in general calibration because it is relevant in the presence of no response. Why? Because finally, we have different properties by using different choices of F. And this is underlined into a paper in Journal of Official Statistics in 2016 of Aziza al-Lesage. You'll hear a lot of times the name of Aziza today. Okay, and you have the chance to have David Aziza here in the room because maybe he can add some other features if he wants. And of course, different forms of capital F, for example, X or 1 plus F, provide different estimators that are not asymptotically equivalent to the one based on linear form like in the classical calibration. And of course, I think that we don't have an explicit model. Okay, so from this point of view, I share a little bit the point of view of Deville and Cott, because we assume that PI is implicitly equal to 1 over capital F, the adjustment factor. And of course, in practice, the functional form of capital F is a question of guessing because there is no way to determine this form such that the inverse of the response probability is equal to capital F. And related to this, in the paper that I indicated, Aziza and Lesage showed by Monte Carlo simulation that an incorrect functional form of F in one-step calibration may result in significant biases. For general calibration, we don't have this kind of, let's say, results, but probably it's the same. And a last feature here, I don't know if you remarked, the number of calibration variables should be equal to the number of model variables, okay? However, there are some extension of this. For example, in the paper of Chang and Cott in 2008 or Cott and Liao, more in 2017. And I will come back on this problem a little bit later because I will use again this result from the paper of Chang and Cott. Now, how is possible to estimate the variance? We can use, for example, the reverse approach, and this was used into a paper again by Lesage, Aziza, and Dotfeuille in JASA in 2019. Cott also suggested to use jackknife method and two-phase approach to estimate the variance. He also reconsidered the problem into a second paper by Cott and Chang. And we also discussed this in our papers, Giovanna Renali and Andrea Neri. Okay, concerning the consistency of the general estimator of the total, for example, it was in the paper that I already cited, Cott 2006 and survey methodology under a linear regression model that is given here, okay? Cott uses this condition that is given here concerning the error terms, but if yi contains zi, this condition is not anymore fulfilled. And it is another point of view of Lesage, Aziza, and Dotfeuille, okay, in this paper in JASA in 2019. And the authors use an asymptotic framework, and the proof of the consistency is based on several assumptions. There are two main assumptions that are used here. It is this one, okay? So if X and R are independent given Z, so the variable Z explains the response mechanism, this covariance is 0. And there is a more technical, let's say, condition that is given in the second part here. And the second condition here is already fulfilled if Z contains Y, because if you condition on Z, Y is fixed, and you obtain here a covariance that is 0. And I have to introduce two important features of this general calibration. Why? Because in the case where Z is equal to Y, okay, so I take Y to be our model variable. There are two important ingredients which are for the efficiency of the general calibration estimator. First of all, it is a large correlation between X and Y in order to have a reduction of the variance. And the second one is the independence between X and R conditional on Y for bias reduction. And I'll show you some examples in order to exemplify the two, in order to see how it works, this, let's say, generalized calibration estimator. I'll give some examples based on Monte Carlo simulation. In this case, we estimate the population mean. We use the census. So from the population, we select 10,000 sets R with using Poisson sampling with probabilities pi I. And we have a population of size 1,000. And we use 4 different settings. In the first 2 settings, there is a correlation between X and Y. Setting Y and a high correlation. Second to, let's say, a correlation that is not so important. What is new here, and it is a variable U that is introduced. This is an example that it is inspired from the paper of Lesage, Aziza, and Dotfeuille in 2019. So what is new here? We have X, we have Y, but also a U variable. X and Y are independent, but you observe that in this moment, there is a relationship between X and U. And so please remember this YU variable here. And finally, in setting 4, X and U are independent. Concerning the response probabilities, in the first 2 settings, I will assume that the response probability depends on Y, and we have this logistic 4. In setting 3, the response probability depends on Y, but also in this new variable U, which is like a shadow variable. And in setting 4, the response probability are uniformly 0-1 distributed, okay? And what I assume here, I assume that Xi is the vector 1, X1, Zi is 1, Yi, and in each run, the estimated response probability has the form that is given here. So only in the first 2 settings, the response probabilities are respected. And we try to see what's the matter, take into account each case. Okay, so first of all, in the first setting, there is an important correlation between X and Y, 0.75. The 2 conditions that I showed in the beginning are fulfilled. The first one was about the correlation in order to reduce the variance. The second one was about the independence between X and R given Y in order to have a small bias. So here the 2 are fulfilled. And we compare 5 different Hayek type estimators for the mean. 1-step, 2-step calibration, general calibration, uniform. So here we have uniform response probabilities, and the estimator that cannot be constructed in practice using the true P. And the blue line represents the true value of the parameters. And of course, we can see here that our generalized calibration performed very well, okay? However, in terms of the bias, however, it's not so obvious, but we can observe that there are some outliers here, and the dispersion is larger than in the case of the 1-step calibration. All the time, I'll compare the general calibration with the 1-step because we have the same, let's say, functional form. Okay, so why we have this problem with the variance? Because if you want, if we compare the weights in the case of 1-step calibration and in the case of general calibration, we always, or in most of the cases, we will have this problem here. The dispersion is higher in the case of the general calibration than in the case of 1-step calibration. Okay, and from here we have a larger variance of the general calibration estimator than of the 1-step calibration. But finally, since the bias is very small, we'll have a smaller mean square error value. Okay, so this is a case where the general calibration has a very good behavior compared to the 1-step calibration estimator. Now in the second setting, I will reduce the correlation between X and Y. Now it's only 0.35. Okay, and what's the matter? The second condition about the bias reduction is fulfilled here. But if you observe, I have a higher variance for the general calibration compared to the 1-step. Okay. And why? Because I have this correlation that is smaller compared to the previous case. And finally, we have the case number 3. Here we have a bias amplification. If you remember, this is a case where we used a shadow variable U. And in this moment, the second condition is not anymore fulfilled. It was a condition about the independence between X and R given Y. And in this moment, we observe that our general calibration have a bias amplification because this second condition is not anymore fulfilled. And finally, the worst case is the case where I don't have correlation, okay? And the response probability does not depend on Y, okay? So in this case, our general calibration is, has the worst behavior. And of course, from here, we have to understand that we cannot simply apply this calibration estimator, general calibration estimator in all the situations because it is possible to have this kind of situation. Okay, and now I mentioned in the beginning that this general calibration is probably less known. Why? Because we don't have software implementing this. However, from many years now, we celebrate this year 20 years of package sampling that I developed with Professor Yves Tillet. Now we have the version 2.11 this year. And from in this package, we have a function called the GenCalib for general calibration with 4 methods. Okay, so we have the linear raking from where we can obtain also the form of the logistic response probabilities. We have truncated and the logit. And in the logit case, we have something that is less known again. It is what we call the general exponential adjustment. This was discussed by Cott in his paper in 2006. It is, first of all, introduced in another context by Folsom and Singh. And what is new compared to the classical calibration here? Of course, we have the bounds for the adjustment factor F. Okay, but if you see here, there is a constant C. Okay, in the classical calibration, this C is equal to 1. But the idea is here to have something, let's say, more flexible for the estimation of the response probabilities. And for this reason, we can have another value for C. So for example, if C is equal to 2, the idea is to have the adjustment factor center around the value C equal to. So finally, to have the estimated response probabilities centered around 1/2. Okay, so in this moment, we give more flexibility for the response probabilities. And we have some nice properties. So for example, if the lower bound is 1, C is 2, and upper bound equal to infinity, what we obtain is something close to 1 plus x, which gives us the response probability in the logistic form. Okay, so it is possible to use this more flexible form of the logit method. Okay, of course, in this function, if you simply introduce z equal to x, you obtain the calibration estimator, but where we have this flexibility for C. And now I move in the second part, okay, and since in the third part, I will talk about non-probability samples, and all the time we related this with a low response rate in probability samples. I will talk a little bit about something which maybe is related, and I will start with the international experience about this, because in general, no respondents are metropolitan residents, single people, widow people, person of foreign origin, okay? So we can underline two kinds of characteristics of respondents: general, which are used, for example, in most of the cases, like age, gender, ethnicity, race, civil status, but also a kind of specific characteristics, like, for example, personality traits, motivation, relevance of survey topic, attitudes. And this is, let's say, something that is less used. And since we observe that we have low response rates in probability samples, the question is, does the propensity for response in survey really exist? And perhaps, but it is not observable. It is a latent variable. And it was called, for example, tendency to respond to the survey into a paper by De Menez and Bartolomeo. And with Giovanna, we called this will to respond to the survey into a paper 10 years ago in survey methodology. And what is the idea here? The idea is to weighting through latent variable modeling that is expected to perform well under non-ignorable no response, where conditioning on observed covariates is not enough. And for example, in our paper in 2023, so with Giovanna Ranalli and Andrea Neri, the idea was to use latent variables and model variables in general calibration. So we can use this kind of will to response to the survey that is a latent variable. And this can be estimated by using special latent models like item response models. This is a kind of, if you want, a logistic regression, but where the variable is not observed. Okay, it is a latent variable. And we can use this, or for example, you can think that in the case of surveys about politics, we can have a latent variable called attitude towards politics, which can better explain the response probability of a unit to answer that the survey than any observed variable. And I will show an application that is close to official statistics. It was done on the data of the Italian survey on household income and wealth that is conducted by the Italian Central Bank every 2 years, and the collective information on two sensitive topics, income and household wealth. Here, Y is household wealth. And in order to construct latent variables, we use what we call manifest variables. And the manifest variables that are used here contains classes of Y, wealth classes. It contains, for example, the number of total attempts needed to make the interview and the other variables. So in total, 12 manifest variables. And from here, what we do is to construct 5 latent classes of responses using the 12 manifest variables. And in this moment, what we created is a kind of probability clustering approach. And we employed this as homogeneous response groups. And the predicted latent class membership were used as model variable in the general calibration. And there is a problem in this moment. Why? Because if you remember, we have the usual assumption that the number of X variables, calibration variables, is equal to the number of Z variables. And here it is not anymore satisfied. So we have used what is given in the paper of Chang and Kot, an extension of this. So in this paper, the authors propose several traces of a matrix W that is a symmetric positive definite matrix and compute the weights like as we have seen before. But in this moment, they minimize this quantity that is given here based on W. And this allows to have more X variables than Z variables. Okay, but the problem that is here, the calibration equations are not anymore satisfied. And what we have used, it is a double calibration. Here we have 18 calibration variables, and we have a less number of model variables. We applied the two calibration, a double calibration. So in the first step, we use this method of Chang and Kot, and the weights in this moment depends on Z. And we use a second step where we calibrate with all X variables. So in this moment, the final weights have this double adjustment factor here. The first one depends on Z, and the second one on X. So in this moment, the calibration equations are satisfied. Okay, and some results, okay? And you'll see that the results that are shown now are related to what I showed in the simulation. So first of all, here, as I said before, we want to estimate the mean of the household wealth using different estimators. We have in total 6 estimators here. All are Hayek type estimators. The first one is the Hayek estimator without no response adjustment. The second one is a two-phase estimator where the response probabilities are estimated by using a logistic regression model that uses covariates known also for no respondents. Next, we have the classical calibration. And at the end, the second part, we have 3 generalized calibration estimators. In number 4 uses the 5 latent classes. Number 5, the 12 manifest variables that we have used to construct the latent classes. And number 6 uses the classes of Y. So the variable of interest. And I'll start with the last column here, okay? So if you compare the 3 generalized calibration, okay, it seems that the number 5, where we use latent classes, performs well compared to the others, okay, in terms of the CV, but also in terms of the standard deviation of the weights, okay? But if you compare this with the classical calibration, I will have a higher CV for the estimator number 5, okay? Why? Because we already have seen this in the case of simulations, okay? In the beginning, I used the important correlation. The bias was of K, but the variance was greater. So in the end, the mean square error was smaller for the general calibration than for the classical calibration. Of course, here we don't know the true, okay? But however, there is a macro estimate that was used here, and this was computed by using outside sources. And this macro estimate of the mean with the value given here was considered to be reliable by Central Bank of Italy. And if you see now the second column here, ratio to macro estimates, all the generalized calibration estimators provide higher values of the ratio. That means we are closer to the value that is given here than in the case of the classical calibration. Okay, so the error that is produced is lower than in the case of the classical calibration. Okay, and from this point of view, we think that the calibration, general calibration number 4 is the best one in this application. Okay, and now I will move in the third topic related to non-probability samples. Okay, and I will start with the definition. So what is a non-probability sample in this case? It will be the following case. Okay, it will be a subset of U. The selection of the sample itself is not random, but the decision of a unit to answer the survey questionnaire is the outcome of a random experiment. And we have an indicator variable denoted by I, which is indicates the participation of a unit to this survey. And this indicator takes value 1 with unknown probability of participation. NP means non-probability, okay? And 0 if not. And finally, the non-probability sample SNP is the subset of units from the population where this indicator is equal to 1. And the variable of interest for each unit in this subset. And what we do usually is to assume two main assumptions. So first of all, the participation probability does not depend on the variable of interest. I written like this because I would like to underline why. Okay, usually we write the probability of participation depend on X. Okay, and the second one, we have the probabilities of participation larger than 0 for all units in the population. Okay, now there are a few papers which consider the first assumption not fulfilled. And for example, it is a little bit discussed into a review paper of Jean-François Beaumont in 2020. And afterwards, we have some other papers. And in the case where the second assumption is not fulfilled, we talk about undercoverage. And in this moment, we suppose that we have a kind of subpopulation of domain UNP that is taken from the population. And Changbao Wu, in his paper in 2022 in Survey Methodology, underlines two types of UNP, an deterministic UNP, and in this moment, units that characteristics will never be included in the non-probability sample. For example, people who do not have internet access. And there is a second case, the case of a stochastic UNP. And in this case, this UNP is a random sample from U. And Changbao Wu underlines that finally this UNP is defined by this condition where the participation probabilities are larger than 0. And this is also used into a second paper, Chen and al. In 2023, again in Survey Methodology. The author used what they call a measure of accessibility dependent on the participation probability, which takes into account only X. And they define this kind of subdomain or subpopulation UNP in the deterministic case. And there is also another point of view, and this is given into a paper of Savitsky and al. In Statistics in Transition in 2023. And this makes the connection between what I showed before with the latent variables and non-probability samples, maybe. So in this moment, we can make a connection between undercoverage and latent random mechanism. So there is the word latent that is used again. And in this paper, the author assumed that the non-probability sample is taken from this domain UNP and is governed by an underlying latent random mechanism with unknown participation probabilities depending only on X. And they also provide an application for official statistics. So if you are interested, I recommend you to see this paper. And I think that in my opinion, this definition of UNP may be related to the existence of latent variable willing to respond to non-probability samples, which will depend both on X and Y. Why? Because I think that, for instance, willingness to participate in this kind of surveys is often driven by interest in topic, survey mode, web, app, phone, past experience, incentives to participate in surveys. This is also very important, okay, the gifts. And also personal traits, personality, civic engagement, but also for maybe on age. Okay, so I think that is a mixture between something that is latent and something that is observed. And now for the case of non-probability samples, we can underline cases. So as I said before, SNP will be the non-probability sample. So in the first case, we can see this subset that is taken directly from the population U. In the second case, we have this subset taken from the domain UNP. Or we can have, as we have seen in the last years, the connection with a probability sample. Okay, so in case 3, I have our non-probability sample, a probability sample. Okay, I have an overlap here that is assumed. And in the fourth case, I also introduce the domain UNP. So our non-probability sample is taken from this domain. And since I used afterwards general calibration, I consider an overlap between the two samples. Why? Because if you don't have this, okay, we have a lot of problem of convergence. And I will consider the two cases that are given here. So case 3 was discussed in the paper of Beaumont in 2020. And Jean-François advocates the use of general calibration when the participation probability depends on Y and discusses some conditions of application of this estimator. And I will also use this idea of a domain that is taken from U in case 4. And now assumptions that can be used. Okay, I will work directly with case 4. So I propose 6 assumptions. So first of all, the probability of participation depends on Y. All the units in this domain have a positive participation probability. The indicator variables are independent given Y. There is a probability sample with unknown Y that is considered. We have a set of auxiliary variables which is available, and we have a link regression model that holds in the overall population. And finally, what we have seen in the beginning is a condition that X and the participation indicator are independent given Y. Okay. And of course, if UNP is equal to U, we come back to case 3 that was indicated before. And now what is the idea? The idea is to use the calibration equation that have been used also in Beaumont and Chen and all in 2020. So what we have here, we have the part concerning the non-probability sample, okay? And the part concerning the probability sample. Of course, in the case of the probability sample, I assume that I know the first order inclusion probabilities, okay? And by using general calibration, we are able to provide an estimation of the participation probabilities. And next, the general calibration estimate of the total can be constructed by using the usual formula, where in this moment the weights are equal to 1 over pi hat, or we construct the estimator for the mean. It is a Hayek type estimator. Okay, and of course here we have 2 important problems. We have the selection bias and under coverage. And I think you should be realist. The problems are still there, okay? They are not eliminated. But what we try to do in this moment, we try to reduce their impact using the general calibration compared to the naive estimator and the classical calibration, okay? In the case where I have the conditions that are given before, and also I assume that I have a relatively large size of UNP. So this is an assumption which should be also included in the set that I indicated before. And I will show some results. So I used as before the logistic form of the participation probabilities depending on Y. We want to estimate the population mean, okay? So overall population U by using the general calibration. And this is compared to the naive estimator, so the sample estimator, and to the one-step calibration estimator, which uses only X. And what I provide here, I will use a population U of size 1,000. I will assume, as I indicated, the response probabilities using Y. And we have 2 simulation settings. In the first setting, I have an important correlation between X and Y. Okay. In the second one, there is a less important correlation between X and Y, 0.35. Okay. And I also have 2 cases, the case where UNP is equal to U, and the case where UNP is a stochastic subpopulation of U, with 2 options. In the first option, I use a simple random sampling without replacement. And in option 2, this UNP is seen as the basis of a lengthen process for selecting a non-probability sample. So it will be a systematic sample with inclusion probabilities proportional to the first principal component of X and Y. And I also assume a size of UNP equal to 500, okay? So I will reconsider this UNP in each run, okay? In the case where this is stochastic. And also in each run, I will use a probabilistic sample SP, which is a systematic with inclusion probability the absolute value of X and the size of 400, while S&P will be considered in each run to be a Poisson sample with probabilities of participation that depends on Y. Okay, and some results. Okay, more or less, you'll see that we have, let's say, the same behavior of the general calibration like in the case of no response. So in the first setting, I have an important correlation between X and Y, 0.75. Okay, and in the first part here, I consider that UNP is equal to U. I take into account the absolute value of the relative bias, okay? And we are able to reduce this by using general calibration compared to the naive and the classical calibration, okay? And also the root mean square error is smaller in this case. Now, in the case where we have the first option, that means this UNP is simple random sampling without replacement from the population. More or less, we have the same behavior. Of course, here we have higher relative biases because I use only a part of the population. And also this is shown when I use the root mean square error because I will have higher values of the root mean square error. And finally, in the last option, that is more complicated options because I assume that UNP depends also on Y. We still have a good behavior of the general calibration in terms of absolute relative bias and root mean square error compared to the other two estimators. But in the second setting, where I reduce the variance between the correlation between X and Y, only 0.35 in this moment, let's say the situation changes. Why? Because, for example, in the case where UNP is equal to U, relative bias is still okay for the general calibration, but the variance is important, and the root mean square error is the same as for the calibration, okay? Now, in option 1, again, we have the same situation, okay? And also in the last case for option 2, okay? So it seems that, as in the case of no response, this correlation is quite important for this problem of the variance, as I indicated in the first simulations. And now I'm almost at the end because I will try to conclude. So we have seen that this generalized calibration method is very useful for dealing with non-ignorable no response at the unit level when the response probability depends on the variable of interest or other variables which are unknown for non-response. And for example, it can be used for service-sensitive topics like income, household wealth. In what I showed, I consider that the response probability depends on Y, and we have seen two conditions: a correlation between X and Y, which should be high, and the independence of X and R conditional on Y. Okay, the first one is related to the variance, the second one to the bias. Okay. And of course, if these conditions are not met, I will have, for example, increase in the variance in the first condition and related to the first condition, and the increase in the bias for the second one. And of course, we cannot use this calibration, general calibration estimator in all situations. And for this reason, I underline that caution should be exercised when applying this general calibration estimator, and it should always be compared to the calibration estimator. And in what concerns extension to non-probability sample in combination with a probability sample and the linear model between Y and X, which holds in the whole population. Okay, here we have seen that we can apply different assumptions which differ from those usually employed. And this, let's say, is good, it's nice. And I think that we can use the general calibration estimator to outperform the calibration estimator and naive estimator in terms of absolute relative bias and mean square error, provided that some conditions are fulfilled. So, of course, the participation probability depends on Y. We have a good level of correlation between X and Y. We have the independence of X and Y conditional on Y, and this is related again to the bias. And we have a sufficient size of UNP, okay, because we have to be realistic. If this UNP is too small, it doesn't work, okay? So this is more an assumption. And finally, also, I think that the mechanism by which UNP arises from U is not solely dependent on X, okay? And this is reasonable if we take into account our assumption that the participation probability depends on Y. And I think that this calibration estimate, general calibration estimator, deserves to be studied more in detail because it offers interesting perspectives for non-probability samples. Thank you very much for your attention.
Thank you, Professor Mattei, for your talk and for your effort to stay, however, in the time that was planned. So double congratulations. And I hope that there are questions from the floor and also from the people that is online. Is someone coming with a microphone?
So he's not here.
May I pose a question?
Yes, please.
Maybe I wasn't, I couldn't grasp everything you said, but I was very much involved in what you say in your slide 36, and indeed I should like to understand more about the two basic assumptions that are made in that point, and which are let's say, the differences between these two main assumptions and the other sets of assumptions that you proposed later. Maybe those are the most important.
Yes, those are most important because, first of all, we assume afterwards because the participation probability depends on Y, okay? And this is a case that is difficult to manage. Okay. And as I said, there are a few papers where this assumption is not fulfilled and it is discussed. And while the second one, I think it's an assumption that we don't like a lot because we assume all the time that the participation probability are greater than 0 for everybody. And this is not true. This is not true. And for example, if I have a web access, I will not answer this kind of non-probability samples. Okay. So assuming that we have a positive participation probability for everybody, this is too much, I think. And I think that many of the participants here share the same opinion. Okay.
Well, thank you. Maybe with Professor Zhang as a surely question.
Yes, well, thank you for the talk. Very interesting, I think. I have actually, now you have on these slides, I had another question, but now you're on these slides, I would like to ask a question on these slides too. So I have two questions. First, I will take this one. So I'm wondering, so when dealing with so-called non-ignorable non-response, for many decades ago, people already started to do an approach which is called just explicitly modeling the non-response mechanism by including Y into a model. So explicitly build a model, right? So now you mentioned, for example, if I do the traditional calibration, there is a kind of an implicit PI hat involved. I'm just so there is kind of, instead of modeling MAR two-step, I'm ignoring it, but then there were some pros and cons and things like that doing that. There's potential danger. But actually, I was wondering, compared to some of these approaches, not everybody is doing that, but some of these approaches at least is also explicitly modeling the response, taking into Y and X and so on. So that approach versus generalized calibration, again, there is kind of a parallel to, I'm dealing with this somehow implicitly, I'm dealing with this explicitly. Okay, what is in pro and cons of your opinion? But I'm sure this is just your experience.
For the moment, I don't have an answer, of course, because if not, I can present something. Okay, this is, let's say, it is maybe a task for the future, okay, to compare with other methods, okay. But for example, in the last case that is given here, okay, so here the authors use logistic regression models, okay, and they use, for example, Y taken from the probability sample, and they suppose that Y is known probabilistic sample. Okay, so it's quite a different kind of assumption there is behind. Okay,
but I don't want to sort of but you know, recently Danny's been talking about this, and he's emphasizing the point that you can even do some kind of model diagnostic and things like that.
For the moment, I don't have an answer to this.
Yeah.
Thanks for your
So
question.
leave this point. The other question I had originally was actually your equation 5, I think.
5 was before.
So that's where the setting you have a sort of a UNP. You have a UNP, you introduce a UNP, which could be a subset of the U, and it is determined by the latent variable Z, your equation 5.
Yes, I'm searching for 5.
If I remember.
Okay.
Yeah.
Yes.
So the probability, the PNPI is actually going from the SNP to the UNP, right? Not from the SNP to the U. It's because it's the UNP now, right?
Yes, of course.
So why do you equate this thing with the population? Because it's coming from SP pi I, that total refers to the whole population. I understand you are saying that, okay, I want this to be substantial and everything. So it's not, UNP has to be substantial compared to U, so it's not exactly the same. But anyway, this is a two absolutely total, which seems to be not on the same level anyways. Like
yes, of course. But okay, if you remember my picture here, okay, I assume that the most of SP is from outside of this UNP. And for this reason, we have to have this linear regression model that holds in the whole population, if you want. Okay, so this is a hard condition, finally, a hard assumption.
would there not be, I'm just, okay, you obviously you have reasons for doing what you say. I'm just thinking why about this equation. Or would there be other ways of introducing these calibration equations in a way that is kind of taking account of more nuancedly in a way how these UNP compared to how UNP compared to U, how SNP compared to SP compared to U and UNP, you may taking a consideration of this.
Yes, they are not on the same level, if you want. I agree with this. Okay, but I think that this UNP is kind of subpopulation of potential people that are maybe will answer this non-probability sample, and this is the difference between the two. Okay, and if you see my assumptions, for example, I don't take into account here what is outside of UNP. Okay, so I don't define the participation probability outside of UNP. Okay, I don't take into account this kind. Maybe it's there, but I'm not interested on this. Okay, so for the moment, it is not defined. This is my point of view. Okay, so I underline this idea. I have a subpopulation of potential participants. Okay, and not the overall population. Okay, and I think that this idea of undercoverage is very important, this kind of non-probability samples. Thank you.
There is a question from Dr. Piero Falorsi here in the first row. Thank you.
Thank you, Alina. First, I want to thank you for your lesson. It was comprehensive, clear, very, very interesting masterclass. I have a technical question that I don't know if this is because when we use standard calibration for estimating the variance, we use asymptotic assumption that of the variance of calibration may be estimated by the variance of the Greg estimators. We use this assumption. There is some asymptotic results on the generalized calibration for the variance of the general.
Yes, in the paper of Lesage, Aziza, and Dotfeuille in 2019, you have this kind of conditions. Okay, so they use a reverse approach, but we have this kind of conditions which are discussed.
Thank you.
Are there further questions?
Thank you, Alina. First, a clarification on your last simulation set, which is I didn't get the difference between the two options on UNP in the last simulation. You have two, option 1 and option 2.
The first one, UNP, is simply random sampling without displacement. Okay, so it does not depend on Y, let's say, and in second option, it depends on Y.
So again, it's not something deterministic, but there's it's another.
UNP is random, yes,
Okay,
stochastic,
and then
consider a need to run, yeah.
Thank you. And then maybe just 2 comments. I'm not sure whether Lichun's question was relevant, but maybe in those papers they were assuming case 3. So indeed, if you calibrate
case 3 or 4?
Case 3, I think.
Case 3, it was
if you go back to so I think that if you just calibrate the total of S and P and of S, then you're actually calibrating. You're assuming you're calibrating on the same population. So it makes sense to have that equation 5. I think that was a reason for that. Yeah. And then a final comment is when in your conclusion, you said UNP doesn't have to be too small.
Yes. And
I think that this is one of maybe I'm not really updated with the literature, but it's like the first technical justification for the fact that online panels, they just don't work, because there are some evidences. I've read papers in which they try to compare online panels with like classical quota samples, and they always kind of have the feeling that online panels don't work, but there is no explicit proof for that. But I think that it really comes from what you're saying here, is that for online panels, just UNP is too small. And so they keep just sampling from those panels, and that's the reason why they're just not representative.
Yes, okay. This is a strong assumption about the size of UNP, because finally we are not able to calculate it, okay? UNP is there, okay, but finally it's unknown, and then I don't know how to estimate its size, okay? I'm honest for this. So it is more an assumption, okay? And of course, if you try to use this from the practical point of view, empirical point of view, the estimators are very unstable if UNP is too small, okay? So this is, I think it's very important, and maybe it should be added as an assumption here in the list.
Okay. For me, the UMP looks like a 2-stage sampling approach, basically. I mean, there is probably no black and white that you are in the part where you can participate or you cannot. For example, your example with the internet connection, you probably can model if a household has an internet connection or not quite well. And then that's again a probability mechanism. So the first step is you have to model, is it possible for a person, a household to participate? And the second step is you model if the household actually participates. So, I mean, for me, it would seem quite logical that you do that explicitly if you have variables available that explain this mechanism. I mean, if you don't have anything that explains it, you're probably out of luck. But if you have variables available, for example, like regional variables of where the household is located, what's available, the household composition, things like that, then it's quite logical that you can model if they have internet access, if they have a Facebook account, whatever the setup is. Is that an alternative?
Yes, of course, but just to comment on this, okay. But I think that sometimes we are not able to catch this, okay? And for this reason, I added this idea of a latent random mechanism from which determines finally this UNP domain, okay? So I think that the problem is much more complicated than we think, okay? And the reason to participate to a non-probability sample is complicated because, okay, here I take into account persons, but maybe for the households it will be similar. Okay, there are different reasoning to participate or not to this kind of non-probability samples. Okay, so from the beginning, it's we have two distinctions between units: a potential participant and the others. Okay, this is my idea.
Professor Aziza.
Thank you, Alina, for your excellent overview. I had out of curiosity, you mentioned at the beginning of the talk that, and this is correct, that the choice of F has not been investigated that much in the context of generalized calibration.
Yeah.
So have you done tests? Because if I recall in our paper, we assumed that F was correctly specified.
Yeah.
Have you tried, misspecifying the F function to see what happened?
Okay, misspecification, even here if you have seen, for example, here it's a case where it's misspecified because I assumed here that we have the logistic form as the response probabilities, but in the beginning, we are simply taken from the uniform 0-1 distribution. Okay, so this is a case, okay, it's a extreme case, but it's there. Okay, so I suppose that it's exactly the same problem like in the case of one-step calibration.
Yeah.
Okay.
So you pay a price, big price.
Yeah.
Okay. Thank you.
Professor Pratesi.
Oh,
Thank you.
thank you. Thank you, Alina. My question is more philosophical than technical. And you have written that there is a sort of willingness to participate to a probability sample.
Yeah.
I think that it is a sort of contradiction. This is because in many cases, non-probability samples are observational samples. So there is no willingness to participate or not to participate. Consider big data. You are there because of many other behaviors you have had.
Yeah.
So maybe there should be another term to say that you are in a non-probability sample, but willingness or unwillingness to be. I think that individuals are not so statistical expert in statistics that they can distinguish a non-probability from a probability sample and to be more prone to participate to a standard probability survey instead of a non-probability one. It is just to reflect a little bit on.
Yes, of course, but I think there are kind of professional respondents for this kind of non-probability samples. And as I indicated here, for example, the incentive is to participate in this kind of surveys are very important. Okay, so there are people that received a gift and they participate without problems to this kind of non-probability samples. And from this point of view, this, let's say, factor is very important in this willingness to participate. Okay, this is my idea.
Okay, there is a question from Arno van Delden from Statistic Netherlands.
Yeah.
And the question is, can you explain how you estimate the response probability depending on Y that is not observed in case of no response? I understand that you use latent variables, but I could not grasp it entirely how it works, or that the K are certain assumptions that are made.
Of course, there are assumptions which are made. Okay, I don't know if now I have to come back in the beginning, how it works. Okay, in the classical case, let's say without the latent variables, what is implemented for this general calibration to satisfy the calibration equation is simply a Newton-Raphson method. Okay, so this is done in our package in GenCalib. This is a method that is implemented. So it's a classical way to solve this problem. Okay. Now, of course, in the case where we use latent variables, there is another point of view because, okay, they are not fixed. Okay, and in this moment, okay, some variability is introduced by using this kind of latent variables. Okay, and of course, this is very difficult to manage, and it was one of the main criticisms in our paper. If you remember, Giovanna, I think it was caught. Okay, as a referee. This is a problem that is unsolved, of course, of course. Yes, thank you for the question.
Are there Further questions from the floor? It doesn't seem. Are there questions from the audience that is online? Doesn't seem to be any. And so I think that we can conclude the session even 10 minutes before the forecast.
I don't know if it is a positive or negative point, but in any case, thank you very much.
Maybe
for your
neutral.
attention. Okay.
Okay, thank you. Thank you very much. And again, congratulations for the brilliant presentation. And we have a longer coffee break. Thank you.
Well, good morning. So my name is Maria Giovanna Ranalli, University of Perugia and Advisory Board of ISTAT. Welcome to this second part of the third session on multi-source analysis for official statistics. There were 3 presentations in the program, but one has been withdrawn. So we only have 2 presentations. We have the first one on innovations in the quality of the EU-SILC survey estimates by Stefano Gerosa, and the last one by Fabrizio Solari. Again, I would like to thank everyone who's here and all the participants online. And we will have like 25 minutes for each presentation. And then I will try to provide a discussion for the 2 papers, and then I will open the floor for other questions. So the first speaker, Stefano Gerosa, the floor is yours.
Thank you. I'm Stefano Gerosa, yes, and I'm presenting here joint work with my colleagues Diego Chianella, Michele Dalò, Claudio De Vitis, and Marco Dionisio Terribili. So here is a brief outline of my presentation. We'll present in general terms, the comprehensive methodological review which the using survey is undergoing. I will present you the main issue, our main problem actually, which is precision requirements from Eurostat and the precision gap that you will see our survey estimates presents. And then I will present essentially the main feature of the revision of the ITSILC weight procedure and also its impact. And I will talk briefly about open questions and future work at the end of it. So as I said before, USIC survey is undergoing a very wide methodological review that covers multiple aspects. Main drivers of this push is on the one hand the availability of new data sources in the system of statistical registers, but first and foremost the pressing issue for us of the new and demanding precision requirements for key USIC indicators. In general terms, we are working on 3 different aspects. We are dealing with a revision of our weighting procedure, and essentially integrating data from a fiscal archive, which I will present to you in a few minutes. We are also contemplating our vision of the general user sampling strategy, again, using data from the income register for stratifying households. And finally, we are working also on the development of small area estimation methods for user indicators, but as a I would say backstop measure in case we are not able to respect precision requirements with our standard strategy, and also with the general idea in mind of disseminating user indicators in the future at a small area level. Here is regulation 219, is it 2019, 1017. It will tell you anything, nothing. This name, but for us is the new common framework, new regulation for all of European social statistics, and it sets new precision requirement for user. In general, we are moving from a strategy, a requirement based on minimum effective sample size, to requirement based on exact precision thresholds, which is much more difficult to comply with. Moreover, those requirements are also introduced at the regional level, NAS2 level, for the first time for us. Yeah, you see here, you see the general formula for the required standard error of a particular estimate P. You see that it depends on some parameters and on a measure of population size, which are essentially households. Here you see I have plotted for you the implied coefficient of variation for our leading indicator, which is European indicator, for three hypothetical regions: for a small region, a medium region, a large region. You know, in Italy we have region are very heterogeneous in size and presents a varying level of difficulty to for requirements. And also you see in black the implied coefficient of variation for different level of ROP at the national level. The fact is that in general, new precision requirements are very demanding. For an Europa value around 25%, which is around the prevalence of the risk of poverty or social exclusion in Italy, requested CV is around 2% at the national level, and it is between 5 and 7% at the regional level. But for very large regions such as Campania, Sicilia, Lombardia, requested CV is under 4%, which is hard to comply with. Here you see a table with the compliance with those requirements in the period to 2016-2024. As you can see, the CV of our Europa indicator grew in that period, grew a lot. This is because, as you see before, the response rates went down, or largely down, from around 80% to around 60% in the post-COVID period, in the COVID years and the post-COVID years. And the number of the precision gap, which is the percentage distance between the observed as estimated as standard error and the required standard error, grew from -1%, meaning that we are under the threshold, to staggering 40%, meaning that we are on average across region 40% above the required precision threshold in 2022. Then it went down in the following year, but there are still reason to be scared on our part. Yeah, you see here household response rates, a national and NATS1 level, and you see you see how the response rate went down. We had, of course, we try to counteract this trend. We essentially oversampled incoming waves of because USIC is a longitudinal survey, and every year 1/6 of the sample exit, 1/6 enter. So we have degree of freedom, but only on the entering wave. And because of that, because of this structure, fact is that the impact of the sharp decline in response rate will be felt for years to come. So this problem will be with us also in the future. As I said, this is the general structure of the USILC sampling design. Is a rotational sample design, 6 rotational group, a mixed copy technique. But I'm going fast over this. A classical 2-stage sampling design with a first stage in which municipalities are stratified, and a second stage with households, which currently actually it is not stratified. You will see that we are working on a stratification hypothesis for the second stage also. Current USIC weighting procedure is a classical one. Is a 2-stage weighting procedure. First part of it is no response adjustment. Second part of it is calibration. Of course, each household has a design weight to begin with, which is, and then we adjust its design weight for unit no response at the household level. Until now, we are using a logistic regression model, which is defined estimated for each wave and each technique. Then we go on with calibration. Until now, we use a 2-step calibration. We had a first calibration step using constraint coming from the Labo 4 survey in order to have the two surveys similar in terms of educational level and professional position distribution. We trim the weight after the first calibration step, and then we enter the second calibration step, which is based on essentially demographic constraints. So this is the general structure of our former calibration weighting structure. What we try to do is to change both of the steps. We are trying to change both the no response adjustment and the calibration. As far as no response adjustment is concerned, we try to experiment with the logistic model based not on grouping, because the no response adjustment based on individual response propensity is maybe introduce excessive variation in the weights. This is why we are trying to group the first model is based on logistic. We run a regression model, and then we group a response propensity. We have experimented with a number of grouping strategies, and we chose to use at this stage we chose to use quartiles. We evaluated this strategy according to 2 metrics: concordant index, measuring how well the logistic model can predict and separate respondent and non-respondent units, and the Kish index to quantify how much variability we introduce in weights. Other thing we try is a non-parametric model, CART model, based on classification and regression trees. Which is implemented in R. And we compare results from these models, analyzing percent deviation from required standard error at the regional level. You see here that in general, the best model appears to be the quartile-based model, because it has a smaller interquartile range and a lower median. It goes with a smaller distance from precision requirements. While the non-parametric models seems to obtain inferior results compared to the logistic approach. As far as weighting calibration is concerned, we introduced data from the fiscal archive, which is the Banca Dati Reddituale, because in previous work we show there is ample evidence of non-response bias varying along the fiscal income distribution. And so we decided to introduce constraints for both the number of taxpayers and the fiscal income aggregates using deciles, fiscal income deciles. We decided also to use a detailed decomposition of the upper 1% of the fiscal income distribution, because the non-response behavior of the upper tail is quite singular, and because of the importance in terms of incomes of the upper 1%. So we moved from a two-step approach to our one-step calibration. Essentially, we rationalized the constraint. We moved from 2009 to 175 constraint, introducing also the new constraints on income. We made a lot of trials, and here you see a bit the impact of the new weighting procedure. You see, first, and the column which I am now commenting, there is a large underestimation. This is a number for 2023. There is larger underestimation both of the number of the taxpayers, but this underestimation is concentrated in the lower tail of the distribution. Low income low income taxpayers seems to respond to be underestimated by our survey, and also income is underestimated. And again, the problem seems to be mainly in the lower tail of the distribution, but also the upper tail of the distribution is an issue. You see, we try to calibrate only with respect to taxpayers. And we saw that it was not sufficient to have a good representation of the income distribution. So this is the main reason why we decided to calibrate both with respect to the number of taxpayers and with respect to fiscal income aggregates. So in general, you see, you see exactly what I just described with you. What about the indicators? We introducing the fiscal income data on the calibration lead to an increase in our estimated mean household net income, which is between 1% and 2%. And we also observe a slight reduction in the inequality, essentially. So this is the impact of our new calibration. Income goes up, inequality goes down. It seems it could seem counterintuitive, but you see, the fact is that the non-response was concentrated in the lower tail in the distribution, and correcting for that ends up with a lower inequality. These see well, but it is the efficiency impact of our new calibration. We use the precision gap as the relevant metric. In general, we are quite satisfied for the fact that we obtain around a 10% reduction in the precision gap in 2023, a 7% reduction in 2024, and the number of non-compliant regions decreases. In particular, we are satisfied with, you see, result for Lombardia and Calabria, which are two large reduction in the large increase in the precision of our estimates, And this is essential for us because you see Eurostat demands that the precision requirement to be met if, for large regions in particular. Thanks to this approach, in 2024, Italy would have been compliant with Eurostat requirements with the new weighting procedure. So this is a reason of satisfaction for us. Just some final word about future work, which is the revision of our U6 sampling design. We are working on the use of tax income as a stratification variable for the second stage of U6 sample extraction. So already in 2026, households of the incoming way will be stratified into 7 classes using quantiles. And we are experimenting with the optimal allocation. At the moment, we use a proportional allocation within regional strata. But the reason for hope is that this study has already shown a potential significant efficiency gain due to the certification itself for the estimation of our main target indicator, which is the AROPE. And that's it for me.
Thank you very much, Stefano. The discussion and the questions are all at the end. So now we can ask Fabrizio Solari for his presentation.
Hi, I'm Fabrizio Solari, and this is a joint work with my colleagues Valeria Quondam Stefano, Romina Filippini, and Gaia Rocchetti. And first of all, I will give you a brief description of the motivation and the background of this work. So we have a target variable y, which is partially observed. So just in not for the whole population, but just for a subpopulation. And y is a categorical variable. Furthermore, we have a proxy x of y, which is observed for the entire population. We suppose that the proxy variable x is affected by misclassification. So we have a bias if we use the proxy variable to directly to produce estimates. But we suppose also that the proxy variable x has good prediction properties in terms of microrecords. So for a large part of the population, the proxy variable is equal to the true value of the target variable y. So the goal is to produce an adjusted version of the proxy variable x, namely x tilde, which is both consistent with the target population distribution of the target variable y, but which also preserves the micro-level prediction of the starting version of the proxy variable, that is x. So basically is just we just want to make some sort of editing and change for some micro records the value of the variable x. Okay, just some very short notation. We have the population P, whose size is capital N. We have the two categorical variables y and x, taking values from 1 to capital H. So we have the population totals for y and for x for each class I from 1 to H. Suppose that we also have a sample S with some sampling weights W associated to each individual L. And we can compute the sampling distribution of both Y and X. So we have unknown total for the target variable Y, known total for the proxy variable X, and estimates of capital N Y and capital N X using the observation from the sample. We can evaluate the ability of the proxy variable to predict the true value of the target variable Y using the standard confusion matrix. So we just use, of course, we can observe only the target variable Y in the sample. So we compute an estimate of the confusion matrix, just observing in which unit of the sample we have the same or different value of Y and X, and then adjusting them using the sampling weights. So we have that the row, we have the target variable Y on the row and the proxy variable X on the columns. Of course, we have that the row margin and Y are the sampling distribution of target variable Y, and the column margins are the sampling distribution of the target variable X. So since we are supposing there is some sort of bias in X, we should note that there is difference between capital N hat Y and capital N X. Okay, now our goal is to, as I said before, to adjust some records of the proxy variable X in order to meet the sampling distribution of the target variable Y, but preserving as much as possible the predictiveness of the proxy variable X. So the first step, since we want to change the values of some records of X in the population, the first step is just to make a simple calibration, just calibrating the starting confusion matrix in which we have the column margin equal to the estimate of the distribution of X computed from the sample to the true values observed in the population. So we can use any sort of divergence from any matrix which is consistent with the two couple of margins. For instance, we can use as divergence the Kullback-Leibler divergence, which leads to of course, to the iterative proportional fitting, or Ellinger distance, or L1, L2, moving Earth distance, and so on. So here, then we have to minimize the distance of all the metrics that are consistent with the margins capital NY and capital NX. and we have to find solution as the matrix capital A tilde, which minimize this distance. And the second step of calibration is more linked to our goal. So since we want that the adjusted proxy variable meet the marginal distribution of the target variable y, we just impose that the column margin here, capital N X. Now, this new matrix B should meet the margins of the sampling distribution of the target variable y. So we have the same values from row and column margins. So in this way, the distribution of the of a potential proxy variable corresponding to this confusion matrix will be consistent with the sampling distribution of the target variable y. Now, the problem is that, okay, when I have this matrix B and I have all the values B11, B12, is how can I transform the values of the proxy variable X in an adjusted version X tilde, which is consistent with the new margins. So how can I define the transitions for the proxy variable X? What we propose is to make a minimum number of transitions for the target X, that is finding, and we will see in the next slide in the definition of the minimum problem, which are the minimum number of transitions from X to X tilde that are consistent with the new target margins. Since we have to then apply these transitions to the real population of X, we need that the transitions, of course, must be integer. So we transform both metrics capital A tilde and B in integer values using control rounding procedures. So for instance, the classical proposal made by Cox and Derns or Cozy. So something very, very standard. For the definition of the number of transitions, we define a three-dimensional array, Tijk, where I is the unknown true value of the target variable y. J is the class for the proxy variable X, and K will be the class for the adjusted proxy variable X tilde. So we want to minimize the overall sum of the elements Tijk, satisfying these constraints. So and these constraints are necessary to make the transitions consistent with the starting matrices A and A star and B star. So we have to minimize the sum of Tijk. So find a new three-dimensional array T star, which minimize this sum, and we have to find T star among the set of all the three-dimensional arrays which are consistent with capital A tilde star and and B star. This can be shown is a special case of a three-index transportation problem, and it can be proved that a solution to stars that is tau is not empty exists if and only if these two sum are equal to each other. So the sum of j of the elements A tilde star ij must be equal to the sum for k of the elements B star ik. And this must be satisfied for each class I. And this condition for our matrices, capital A tilde and B star are satisfied since in both cases we have that this sum are equal to the row margin ny capital at. So we for this in our situation there exists a solution to this problem. Once we found a three-dimensional array T star which depends on xi, jk, we can also compute a marginal transition matrix T tilde capital T tilde star in which we just marginalize with respect to index I. So adjust the movement from the class J of the starting proxy variable X to the class K of the new proxy variable X tilde. Okay, now we know we decided how many transitions from either ijk or jk we want to apply for the target variable X. And we have to decide how to apply these transitions, how to select the units for which we have to change the value of the variable X. Okay, the simplest solution is just use the marginal transition matrix capital T tilde star, which depends only from the value of the original proxy variable X, and the class of the final proxy variable X tilde from which we want to make the change. So for instance, if we just have to move T star jk units from the value j of the proxy variable j of the proxy variable X to the class K of the adjusted proxy variable X tilde. Another way is suppose we have there is the availability of a model, and we can use a model, the probability computed from the model to make prediction of the true value of the target variable Y. So in this case, prediction of the index I. So in this case, we can use also the three-dimensional array T star, which depends from the true value I, the class J of the proxy variable, and the class K of the adjusted proxy variable. And for instance, we can predict the class I using the maximum a posteriori predictions, which correspond to the class for which we observe the largest probability. Of course, the maximum a posteriori are produce base estimates if we want to use for for the estimation of the overall distribution. But in this case, we just want to predict the single class I for each unit L. And we can, once we have chosen between 1 and 2, we can apply just simple random sampling, stratified sampling, balanced sampling, or we can use again the model and the probability to apply a PPS sampling using the probability from the model as size. So suppose I want to move a certain number of units from I, J, and I want to move to K, I can make the selection of the units using the probability derived from the model for that couple IJ to have the class K of the target variable. Or alternatively, we can use assignment algorithms or propensity scores. So just something that helps us to select properly the units for which we want to change the value. Okay, now we have an application of this method. We have the educational attainment in Italy. So the target variable are the 8th level educational attainment. The first class is the illiterate, the second class literate, but with no formal educational attainment. Then we have primary, lower education, upper secondary education, bachelor or master degree, and finally the last class is the PhD. The target population are the Italian citizens that were surveyed in 2011 census, and for which we did not observe any attainment of new educational levels. So there is a population for which we expect that the educational level surveyed in 2011 should be the actual also now the true educational level, since we do not have any administrative signals of attainment of new educational level. But of course, the administrative source are affected by undercoverage. For instance, we do not have educational attainment that are attained abroad. Some courses are not covered by sources and so on. So this proxy is affected by misclassification and particularly tends to underestimate the true educational level. The true values Y are the values observed in the 2023 census sample surveys, while the model probabilities are taken from the model used for the estimation of the educational level, and is what was proposed by Marco, Romina Gaia in the paper of 2019. So just to compare the performances of the different setting, we use standard classification measures, that is the accuracy, the precisions, recall. Then we use their harmonic mean of recall and precisions, that is the F1 score. And then we use also something that takes that incorporate the distances between the classes. So it just not consider if there is a mistake or not, but just a quantification of the mistake of the error. So we use L1, L2 function. So, and that of course generate the maximum the mean absolute error and the mean square error. So finally, we have the comparison of the performances of the ability to catch the true value of the target variable from the model probabilities, from the proxy variable before the adjustment process, from the proxy variable after the adjustment process using T star, that is the three-dimensional array, post-adjustment proxy variable using only the marginal matrix capital T tilde star. So just dropping out the index I. So we can see that the model, and this is not because the model was not specified. I think that is a peculiarity of model that of course just there is some sort of shrinkage, so I just lose some ability of predict individual micro-record true values. So the model has the lower values, and they are significantly lower than the starting proxy variable. And the adjustment procedures produce an adjusted version of the proxy variable x, which is consistent with the estimates capital N y hat. So it's consistent with the sampling distribution of the target variable y, and as also an increase of the value for all the measures we defined. Okay, we choose to minimize the number of transitions. Of course, could be not the right solution. It's just the safer. So it is just the safer solution, and we can define the target function with, in a certain sense, try to increase the number of transitions, trying to increase the number of values that fall in the diagonal of the confusion matrix. For the reason we have to define alpha, which is a tuning balancing parameter with for the two objects. We can choose alpha using a Monte Carlo selection for a set of candidates. We can define a grid of candidates, but also we can adopt more efficient strategies to reduce the number of trials we have to do. For instance, ternary search, if we suppose that the final accuracy measure is unimodal, Bayesian optimization, and so on. So the conclusion that the measure adopted ensures marginal consistencies. There are some sort of analogies with optimal transport problems, but here we implementing also individual level transitions. we obtain a new proxy variables that minimally alters the micro level values. The framework is kind of flexible, since we can incorporate domain calibration, diagonal targets, model to assist for the assignment of the transitions to the population. And we can also, of course, we can perform the calibration at the overall level or regional level or subpopulation level. Sometimes we can be interested in making calibration at levels for which the confusion matrix estimated from the sample cannot be estimated in an efficient way. So the estimated confusion matrix can be unstable. So we can also regularize the confusion matrix, adopting some sort of combination with larger area confusion matrix in the spirit of, for instance, small area estimation.
If I can manage myself. Vado? No, come faccio a uscire? Thank you. I will just try to provide a quick discussion for the two papers. So I will just give one slide comparing the two papers, and then some questions for each of them, and then just a final note. So the two papers, they share similarities because they both use administrative data, heavily, and they both use calibration. But there are subtle differences. First one is that the first focus is more on using calibration to increase efficiency, in a sense, while the second talk was more focused on editing, so in a sense reducing bias. So it's using calibration for editing. And there are also differences in the use of modeling, because the first one explicitly used models for reducing no-response bias, while in the second one, modeling is is just assisting while they're trying to find a way of editing, so imputation editing without the explicit use of modeling. So the first paper, we've seen that because of the regulation, there are new and demanding precision requirements for key USILC indicators, particularly for at risk of poverty and social exclusion for NAS2 regions in Italy. Large non-response rates decrease the sample size and particularly increases the sample weight variability. And so this has an impact and some effects on cross-sectional and also longitudinal estimates, because USILC is also used for longitudinal estimates. And the availability of new data sources, particularly income registers, just brought the attention to try to get a revision of the procedures for both non-response adjustment and calibration. And I have to say that this is like a second episode of a first meeting that we already had at the advisory board. So this is like an example of first modifications that the researchers have tried to implement in the USILC after a first meeting. So as far as non-response adjustment is concerned, there are a couple of approaches, moving from having individual propensities, what it was labeled as logistic zero in the slides, two groups based particularly on quantiles. And the second attempt was also with using CART, a non-parametric approach. And so my main questions with respect to this aspect is on model selection, because this is essentially just a problem of model selection in terms of which auxiliary variables to use in the non-response adjustment. And the focus here was particularly on the number of groups for the logistic approach, but also on the tuning parameters for CART. And I can see here a clear bias variance trade-off, because of course, the more groups, the less groups you use for the logistic approach. So say you can just have just one group, I mean, or two groups, three groups. So the more groups you have, then of course, I think the more bias reduction you have, but you increase the variance. So there is this variance trade-off. And similarly, you have the same when you use non-parametric approach. So my questions would be like, so the model selection here is important, and I don't know if it can be done only looking at the variability of the final weights, because of course you will have variability and you will pay a price for that. So it must be something else. And then the other question was, why not trying directly using income and income classes for non-response adjustment? Because also in the presentation, you kept saying no response depends on income, but then you didn't use income in the non-response adjustment. And then the second step, so the calibration adjustment. Previously, they were using 2 steps. Now they're just trying to get a more rational approach, so just 1 step. And it's a combination of 2 different types of constraints for calibration. So the first one is just the essential constraints you need to put for European regulations, and that's something that they have to be there, period. Then the second group is efficiency related, so some things that you plug in to improve efficiency. And then, of course, you improve efficiency, and again, here with the calibration, you may also improve the variability, so it is efficiency. There is a trade-off there. And again, here there's a model selection. Here is with respect to the constraints, to the variables that you use. And what the tools that you've used is analyzing the reduction in the coefficient of variation and the stability of the estimates. And again, here, the model selection is very important. And so my question was, maybe for non-response and maybe for calibration adjustment before you include the income variables, maybe you can use the register for model constraint selection. So for example, if you have to compare model for non-response adjustment, you can try to understand how they predict the variables in the register. So maybe one model is better than the other, and you can actually do that simulating that this is your population. So you can actually try to get a better model selection technique for that. And then a very overall comment. So it's an empty slide, but full of content. In a sense, you're undergoing a deep strategy revision for USILC. So you have design, estimation, and also, in a sense, some smaller estimation. And I think that this is really an important moment in which you can actually take a look at the whole strategy. You're in a very privileged situation. So looking at the design is really important now to get a look at the estimation. So as you said, with stratification or balance sampling, you can just bring a lot of the constraints that you are using now at the estimation stage, maybe at the design stage, to avoid the weight variability. And then also, if there is some smaller estimation requirements, say at province level, if you think about it now that you're revising the design, then you can think about that by, allowing for the design to allow for a reasonable number of observations in advance, so that smaller estimation may still be required, but are less impacted. And then the second talk. So here we have a different situation. So we have a target variable Y observed on a sample S, and then you have a proxy variable X, which is observed for the whole population. but this proxy variable has misclassification and structural bias. So the overall aim is to provide an adjusted proxy, X tilde. So you just want to impute X for the whole population. And so not only within the reference sample. And so the paper proposes a deterministic alternative, because you can do that by imputation, modeling imputation. But they try an alternative. And it is based on two phases. The first one is the two-step calibration that allows you to go from the empirical confusion matrix between X and Y to an adjusted matrix B. And then the second phase is the transition. So once you have understood how many units you need or you want to edit, then how do you select the units for which you actually change the value? So you change the value from X to X tilde. And they actually propose two strategies. They're both based on random selection. It can be just pure sampling or maybe model-assisted sampling. And then there's the application, which is the motivation for this paper, is on educational attainment. So here you have the population census X 2011 and the permanent population census 2023, and you want to just fill in, so adjust the population census X with X tilde for the population in 2023. So that's the aim. So maybe the first is a very naive question. So in the first phase, you move from A hat to A tilde by calibrating N hat X on the population level. And then, of course, you need to keep calibrating your confusion matrix with respect to Y, otherwise you lose the coherence. And then you go from A tilde to B, calibrating N X on N hat Y. And basic, very naive question is, why do you need two steps? Why don't you just go straight from A hat to B and just obtain your B ij's values directly from N hat to NY? And then as far as the second phase, it said that there is no explicit model used. And it's only a random sampling to select the units to be edited. And of course, yesterday Li Chun showed us that even if it's a sample, there is a model behind. I mean, when you choose your sampling method, you've seen me, you showed simple random sampling or even IPS, or even when it's the sampling design is induced by the model that was used before, moving from sort of non-informative versus an informative editing. So your editing is informative in the sense that you are editing just some of the units, and they are chosen not in a non-ignorable way. So if does it have a consequences on the final properties? And then maybe, and this is a very basic question, can we actually move away from integer transition? So the whole point here is just to get an integer transition. So you just select a few units and then you change their values completely. So say I only add like a bachelor degree, and then I will have like a PhD, just integer transition. Is there space for using fractional transition? So why do you really need to just have this integer transition just for a subsample of the units? Can't you just like using models, or even if with not models, with fractional, similar to fractional imputation or calibration, you can just use that integer that you move, instead of just giving it completely to a unit, you can just give it fractionally to units. And then the final note. So the title of the session was Multisource Analyses for Official Statistics. And yesterday we had like a lot of new suggestions for official statistics, machine learning. And then Brunero yesterday in his discussion said we are going through a dramatic change in official statistics. Everything is changing in official statistics. But I would say after this morning that we can have a subtitle for session 3. And subtitle for session 3 is Calibration Die Hard. You can actually see that we've seen a lot of calibration in the whole morning, and calibration is still there, and it's really die hard. Thank you. So now I think I can open the floor for discussion, and then the authors can collect all the questions and they can answer at the end. So questions for any of the speakers?
As compliments to all the presenters and to discuss something very interesting. I have a specific question for Fabrizio. If your approach should be applied to the register, population register, in which education level is registered, is a registered variable. This could imply substantial changes in the register values that has not only an impact on the register, but even on the surveys that user register for benchmark, like so if you want to make a new process, a new methods for registers, you should even study the impact on the, not only on the register figures, but how these changes impact on the surveys that use total registers as auxiliary variables for calibration, because you should impact some changes that are only in surveys that are not caused by changes in the phenomena, but changes in the way you build the register. And so this impact evaluation should be carried out before putting it in the as a standard process for this. Should be a rule for each change in the register, because thank you.
Other questions? Professor Aziza there.
Thank you. I have a question for the first speaker, Stefano. You mentioned that there is a threshold for the standard error. And I think in the table, you show that sometimes you do better, sometimes you do worse. But my question is, how do you actually estimate the standard error in your survey, given that you have, because one of the things is you tried regression trees, and estimating the variance is not that easy. So I was wondering, how did you manage to estimate the variance that to account for sampling, non-response, and calibration?
Other questions? True.
Thank you. Actually, thanks for the presentation. We have more time to discuss tomorrow as well, so I don't want to go to questions that may be too complicated. So it's more, I think it's maybe this clarification. Okay, there's one thing particular with Fabrizio's talk. It's like, seems like you prefer an integer solution, right? Integer solution. You don't want to say I have some probabilities and add up for statistics. You want an integer solution. Can you just explain a little bit the background why this is so important in this context, or preferred, or whatever? Or what are the potential complications people might run into if people went for a fractional solution? I think maybe you could imagine if you go 1 year, next year, and so on, right? That's one issue. The other issue related to that, yeah, I think it's a little bit like, how would you say, your application is educational attainment, right? Educational attainment. So you had a past information, now the new, perhaps not updated in the admin system, right? So in a way, there is direction how this variable can change. I mean, you don't get less educated over time, is my point. So how does that aspect affected in your, because your problem you presented is very general. Anyway, I can do this. But in the context of directional changes that actually can happen in this solution, would this somehow affect your solution, or sort of, that's the only thing?
Thank you. Other comments? Okay. From online, nothing? Okay. So maybe Stefano, you can.
Yes, of course. First of all, thank you for the comments, the insight. And yes, you're right. This is the second step of our of our joint work in trying to increase efficiency of USIC, because 1 year ago we discussed the same matters in the advisory board, and so this is some sort of first result for us. So thank you for being with us along the way. Yeah. First of all, no response adjustment. Yeah, I must confess that I did not take care of the modeling of no response adjustment. This is something that Diego, Chianella, and Marco terribly did. But in general, we use model selection in the sense that we are using stepwise selection to identify relevant variables in the logistic regression models. And yes, we included also categorical variables identifying the position of the individual in the fiscal income distribution. So we use income data also in the no response adjustment phase, but then we let stepwise selection decide which variables are included and which are not. But yes, you are right. I must also say that we essentially concentrated on the objective of variance reduction. Yeah, you know, we did not much of an analysis of a bias variance trade-off analysis, because we were obsessed with taking down increased efficiency, okay, taking down the standard error of our estimates. So yeah, we could better analyze results in terms of bias variance trade-off. Also for calibration, I didn't have time nor space to talk about the trial, but we did a lot of trials. We did a lot of models and with a different calibration set. Calibration variable setting, and so there is some work that I did not discuss and presented here, but I'll show you that under the pressure of the deadline, which is now, we try to do as much as we could. About the variance estimation, yes. Is complex in USILC, also because the European indicator contains nonlinear indicators, which is, for instance, the risk of poverty, which is a nonlinear indicator. So we have to include it also, the linearization of the risk of poverty indicator. We use essentially the Regenesis package, which is developed by our former colleague Diego Zardetto, which allows us to include aspects of design, aspects of calibration, so calibrated, and also aspect of linearization of the relevant variable. Still, I must say that I am not exactly the right one to present the finest detail of it all, because this is something we are assisted in by our methodological colleagues, and I am more of I'm an economist, so yeah, I'm here as an intruder in some sense, but so variance, but I'm quite sure that variance estimation is done carefully, and we try to we have to include all aspects of our sampling design and even on calibration. So that's it, I think, for me.
Okay, thank you, Giovanna, for the discussion and for all the questions. Okay, the first question is why two steps? So why just not moving from A to B without the intermediate level on capital A tilde? The reason is because at the end, we want to produce transitions, so the number of units for which we have to change the value of the proxy variable from the population. So from population which has known total the true NX and known the estimated NX. Probably it wouldn't have changed so much the number of transitions, but just for have a clean process. The second, I can't remember very well, is about the not explicit use of models. So maybe in a certain sense it can be controversial. We made that not to use models, and then we use a model in another phase. And yes, I may agree with you, but it can help to have a better assignment of the transitions in the population. The difference in the table between using and not using the model is about maybe 0.5 in terms of accuracy. So not so much, but it's better than nothing. So maybe if I have a model, maybe it would be better to use it. The last one is about, okay, we have to compute integer values of transitions, since then we want to apply. So maybe your question is, we transform A tilde and B in integer matrices, and then we obtain, of course, in integer transitions. Your question is, you could use a real value confusion matrix A, B, and then compute in real values transitions, and then approximate to the integer in a second at the end of the process. Yes, of course, and I guess that the values could be more or less the same. But another reason, the main reason is that the algorithms are much quicker with integer values with respect to real values. So in terms of computer time, we prefer the first option. But
maybe my question was more connected
Okay.
with also what Li Chun was asking.
okay, then
afterwards.
okay, I give you.
Why integer? Why can you just?
Okay, so just not okay. I've to express my personal view. If I could decide for the overall estimation process, I would stop at the probability step. For all the other variables for which I produce estimates, I never generate random variables, since we do not need them. We just compute overall distribution just using probability. The problem is, maybe it's the same for Marco 7 years ago, that sometimes we have to do something that we don't want to do. So Marco had to produce values and not only probabilities. Now in the revision of this estimation process, I try to say, okay, just make a step back. The model is a good model. It works, and we can just get the model probabilities. But my director said is too late. Now we have produced. Now we have disseminated values, and we cannot make a step back. But I agree with both of you. It's something that maybe we could have avoided. So this is the second also question of Lishun. Okay, now I just finished with Lishun Pierre, and then I try to answer your questions. Okay. You talk about directions. Of course, educational attainment should just either be equal or increase. The problem is that the generation of random it's not it was not maybe a previous requirement, but was so variable from one year to the other. So in the previous process, there were a lot of individuals losing or decreasing their educational attainment. In this way, of course, since it's deterministic, there is the only expected individuals for which we observe the decrease of the educational attainment are the individual that for which this decrease is observed in the source. So of course, if the source has changed, maybe it's a correction or whatever, we incorporate this change in our editing process. Piero, okay. Okay, you say is dangerous from one year to another. Okay, it could be a problem. Okay, it could be okay. We can distinguish between two types of views of the educational attainment in register. If you want to use the educational attainment for calibration, for instance, in many surveys, I know they do it. You just need the estimates at provincial, regional level, and so on. And so this is not a big change from the previous estimates. They are consistent with the previous estimates. If we want to use at individual level, yes, of course, you can have different individual level values, but the new values suffer less than the variability I explained that was generated by the previous estimates. So now they are more consistent with the sources, and they tend to be more stable from one year to another. So maybe from the first year in which we use this approach, that is 2023, we have some differences with 2022, but from now on we have more stable estimates. And so this aspect, I agree with you, could be a problem, but it's something that we got to pay if we want to change the process.
Thank you. Thank you very much to the speakers. Oh, one final comment. One final comment from, I don't know where the microphone is, there.
This is just to defend the model of probabilities that, okay, the problem that there was some, let's say, decrease of educational attainment level, it was not due to the random choice of the model, of course, but because the data observed in some cases show that some people had a level that was lower than that of 2011. And that was for, I mean, we assume that was an error. Also, in the case of this kind of correction, if you assume that your survey data are without error, and so you use that for editing, for changing, localizing error, whatever, in your register data, if you have in your survey some data that once are linked, they show a lower level, of course, you should change the data, decreasing the level. So we can discuss about that. I don't know if it's clear. Joanna, you say. That's just to, I mean, my point of view.
Thank you. So I had hoped I could have saved some minutes for lunch, but indeed we are finishing sharply at 12:20. Just one announcement.
I've got just a little clarification about the total no-response model, just to answer, because yes, we used the income in the total no-response model as a variable, so not in classes, because in the design phase we did and it was extremely difficult. We went crazy dividing in classes that variable, because it means that you answer to another question, okay? And sometimes this variable was significant, sometimes not, because we studied the model for each wave and each technique, so copy and cutting. So just to clarify that, okay?
Thank you. My final note is that the proceedings from the third workshop, so from last year, are now available online, and you can freely download those from the website of the previous edition. And now enjoy your lunch, and we will see here at 1:40 p.m. Thank you again.